Oh, wow, they changed it with the new version. All right, so let me go to a screen share. I'll close this. All right, one thing I forgot to mention in my short introduction was reminding you that 1 atmosphere is 760 millimeters of mercury. The 760 does not change your significant figures. The 273 with Kelvin does, and someone asked a really good question earlier, why is that? And that's because the 760 was kind of was defined, where the 273 was determined experimentally. All right, so let me just go ahead and go through these. So what you want to do with these types of problems is really, be diligent about, making a little list at the beginning. So, for example, for number 1, we have new pressure. So we have 2 sets of conditions here. So we have P1 is 1.65 atmospheres. The volume that goes with it, V1, is 5.0 liters. Another student asked, does it matter which one you call P1? And the answer is no, but realize that the 1.65 and the 5.0 are the same set of conditions. So if you call that P16, it doesn't matter what you call it, but this pressure and this volume should have the same subscript. P2 is what we're trying to find. And V2 is 1.65 liters. All right, so then we can do this. We have 2 sets of conditions. Now, some people can just look right at it and do the canceling out in their head. In this case, since I'm going to write it out just this once, there's no info about N and T, we can assume they're constant. So that means I can cancel them out. That means N1 equals N2 and T1 equals T2. So that means I can cancel them. And so then we have P1 V1 is P2 V2. And then at this point, it becomes algebra. P2 is going to be P1 V1 over P1 V1 over V2, which will be 1.65 atmospheres times 5 liters. Whoa, what did I just do? Oh, that's right. I just realized my numbers are the same. That's fun. 1.65 liters. So this one's going to be 5.0. I don't even have to do a calculator on this one. Is that right? 1.65. Okay. Also, you can do the, does my answer make sense? I squeezed it down to a much smaller volume, so the pressure should go up. And it did. And see how the units work? Make sure your units work. All right. Number 2, new volume of gas at 100. Okay, so we have V1. This is going to be V1 is 3.85 liters. T1 is 373.2 K. Just to show you how I got that, to remind you, 100.0. 273.15. Remember, Kelvin, to convert, you add. Remember, when you add and subtract, it's the decimal place. So 373.15, but that has 2 guesses. So we got to cut it off. So I round it to 2. All right. It says, what is the new volume? So V2 is my question mark. And T2 is 25, which is 298.2 K. So similar approach, we have 2 sets of conditions, P1 V1 over N1 T1. I mean, if you just realize, oh, of course, this is Charles' law, you can go right to it. I found it easier to just remember one thing and then rearrange to taste. So there's no P's or N's, so they get canceled out. So then we have V1 over T1 is V2 over T2. We want to solve for V2. So V2 is going to be V1 T2 over T1, just multiplying each side by T2. And then in this case, 3.85 liters, 298 Kelvin over 373 Kelvin. My Kelvins cancel. And my answer is going to be, there we go, 3.85 times 298 divided by 373. So I get 3.08 liters. I know I'm squeezing it into a small space here, but you get it. Okay, also, does my answer make sense? Whoops. Okay, I cooled it, so the volume should go down. That's number 2. I'm recording, aren't I? Yeah. There's a question in the chat. The 298.2 came from 25 degrees right here, plus 273.15. So put a 25 here, that's where the 298 came from. Okay, number 3, we have a gas. So P1 is 7, oops, let's see, I want to make sure, okay. The chat's up, 715.6 millimeters of mercury. I'm right away going to change that to atmospheres. Just to do it right now, 715.6 divided by 760 is 0.9416.
Professor, do we always have to convert it to atmosphere?
You should get in that habit. You actually, if you're just doing it this way, as long as your units cancel, if you use R, for sure. If you're using temperature, always has to be in Kelvin though. All right, T1, okay, it's 20 plus 273, so it's 293 K. New temperature, if it's expanded to 1.2 atmospheres, so P2. So see how this pressure is in atmospheres, so you want them both in the same unit. And then T2 is what we're trying to find. All right, so same approach, P1 V1 over N1 T1 is P2 V2 over N2 T2. And we don't have volume or number of moles. So that means P1 over T1 is P2 over T2. Now to solve for T2, we want T2 by itself. So what you want to do here, realize if two fractions are equal, then their cross products are equal. So the algebra, P1, I'll refresh your memory, I haven't done a lot of algebra in a minute, is P2 T1. So P1 T2 is P2 T1. And then we can say, I'll just go over here, T2 is going to be P2 T1 over P1. And I think you can see it's really easy. There's a lot of 1s and 2s. So if you take this little step up here, it's much harder to plug the wrong number in. So P2 is 1.20 atmospheres. T1 is 293.2 K. Let's erase that random 2 there. P1 is 0.9416 atmospheres. And so then we do the math. Also, you see the pressure is going down, so the temperature should go down, right? 1.20 times 293.2 divided by 0.9416 as 373 points. Oops, I'm sorry, 373. I'm sorry, the pressure went up. What am I saying? It went from 9.94 to 1.2. 0.7. Actually, this is only going to have 3 sig figs because of the 1.20. So 374 Kelvin. Okay, you can leave it in Kelvin if I get, unless I specifically say Celsius. So you can leave it in Kelvin. If you wanted to convert it to Celsius, subtract 273. So in Celsius, it would be 100 point, it would be 100. And remember, because of the sig figs. So either one of those answers would be correct. Whoops. So, depending on your algebra, this is a lot more algebraic than the stuff that we've done. So if your algebra is a little rusty, right, make sure that if you do each step, you should be okay. I know some of you, it's been a while, some of you are taking like calculus. So, okay, now, new volume of a gas at STP. STP is standard temperature and pressure. And there's nothing special about it, just that because gases, their volumes change a lot, we kind of like to have a certain set of conditions. So that means center temperature and pressure. If I tell you it's at STP, that just means it's at 273.15 K and 1 atmosphere, as many zeros as you want. So in this case, a gas at STP, P1 is 1 atmosphere. I'm just going to give it an extra bunch of zeros. V1 is 15 liters. T1 is 273. P2, it's brought to 1.25 atmospheres. V2 is our question mark. What is the new volume? And T2 is 25.5, so 298, I'm sorry, 273.15 plus 25.5 is 298.6, 298.7. All right, let's just do the math up here. So then we have P1 V1 over N1 T1 is, again, 2 sets of conditions. Whoops, N2 T, Rob, really? 2 T2. And we're not told about the ends, so the ends cancel. So then we have P1 V1 over T1 is P2 V2 over T2. We want to solve for V2. So V2, multiply each side, if you want to do the algebra, multiply each side by T2 over P2. Like T2 over P2 like that. That'll get you that. So then we have V2 is going to be P1 V1 T2 over T1 P2. Right. So now we're going to plug the numbers in. 1 atmosphere. V1 is 15. T2, 298.7 K. T1 and P2 notice that my units are going to cancel. I'm going to come up with volume. That's good. All right, so 15 times 298.7 divided by 273.15 divided by 1.25. I get 13.1 liters. The most common mistake students make on gas law questions is not converting from Celsius, not converting to Kelvin, and switching a 1 and a 2. If you take the time to do this little thing right here, just make yourself a quick little table, it's going to help you avoid mistakes like that. Won't make them go away, but it'll make it harder to make those mistakes. Everything you write it down, you don't have to remember it. It's really easy to switch a 1 and a 2 in your head. All right, last one. This one's a little bit different. Volume of hydrogen, I don't have the degree sign in here, from the reaction. So this is a reaction. This is a little bit different. So let's do this. This is a reaction. Hydrogen is produced, reaction of aluminum with excess hydrochloric acid. So don't see that nomenclature is never going to go away. We know we produce hydrogen gas because we're told. The other product is going to be AlCl3, and then we're going to need a 2, a 6, a 3, and a 2 to balance it. We're told we have 2.50 grams. This is excess, so it's not a limiting reactant question. This is at 55.5 degrees C and 784.6 millimeters of mercury. And we want to find the volume. Okay, now before we do anything, let's convert these. All right, so 55, because we're going to need them in different units. Okay, this is going to be 328.7. And then remember, we divide that by 760, so 784.6 divided by 760. So this is 1.032 atmospheres. All right. Now, what you can do with this is one set of conditions. So if you're not sure what to do, I mean, some people you can just look at it and go, oh, I know, I'm going to have to use this and convert to moles and all that. That's great. But if you're not sure, you can always do the backwards thinking thing. So PV is nRT. That means V is nRT over P. And we don't have N. I'm going to leave it blank. So we're going to have to find the moles of hydrogen. We do have R, 0.08206 liters, atmospheres per mole Kelvin. We have the temperature, 328.7 K. I'm going to move this over now. And we have the pressure, 1.032 atmospheres. So if we had the number of moles, we could do this. So let me just make some space up here. So how are we going to get the number of moles of hydrogen? We don't have the mass. We don't have a molarity and a volume. But what we do have is a balanced chemical equation. So I know that I want to get moles of hydrogen from my stoichiometry. And that number will go right there. So once I get the moles of hydrogen, how am I going to do that? Well, I have 2.50 grams of aluminum. I can convert that to moles. 1 mole of aluminum is 26.98 grams of aluminum. And from the balanced chemical equation, I have 3 moles of hydrogen for 2 moles of aluminum. And I don't have to take this to grams because I only want moles. That's why writing down the units of your answer is very helpful. You won't do an unnecessary calculation. So I get 0.139. And then I can plug that into here, down here. And that's not the answer to the question, though. So I get 3.63, and the answer will be in liters. All right, so just to reiterate this question, this is only one set of conditions. So I set up a balanced equation because I had that information. I rearranged the equation to taste. I want the volume. I didn't have the moles, but I did have R, I had T, and I had P. So to get the moles, that's where I used some stoichiometry. Then I took the number of moles, plugged it into the space it goes into, and then did the math on that. All right, I'm going to stop the recording, and then I'll open it for questions. And you guys know how this works. So let me do this, and then we'll stop the recording.